Okay, so far we've been talking about colligative properties of non-electrolytes. When we have a solution that is an electrolyte, it separates into ions. And colligative properties are properties that depend on the number of particles, not on what they are. So when we have a strong electrolyte, it's going to have a larger effect on freezing point and boiling point, and a larger effect on the osmotic pressure because there are more particles. So the Van 't Hoff factor, given a lowercase I, is the ratio of the moles of particle in solution divided by the moles of formula units that are dissolved. So there's an expected factor that we can get just by looking at the formula of a compound. And then there are actual Van 't Hoff factors, which are not exactly the same because there's some ion pairing that happens in solution. Because it couldn't be just that simple, right? It has to be a little more complicated. So this is an illustration of what happens in solution. Here we've got sodium and chloride that are dissolved in water. So if I dissolve 1 mole of sodium chloride, in theory I get 1 mole of sodium ions and 1 mole of chloride ions. That's 2 moles of particles, right? Not just 1. And so that's what happens with a strong electrolyte. So for sodium chloride, we would expect that that Van 't Hoff factor is 2. Because I get 2 moles of ions for every 1 mole of compound. So that gives me 2. That's what we expect. But there's something called ion pairing, where these dissolved ions are still a little attracted to each other and hang out together in solution. And when they're hanging out together like that, they act like one particle because they're moving together. So the actual Van 't Hoff factor is a little bit less than what we expect. So for sodium chloride, it's 1.9. Magnesium sulfate, that would go into 2 ions. Let's maybe write those out here. So when this dissolves, I get magnesium ions and sulfate ions. 2 ions. So I expect that I'd have a Van 't Hoff factor of 2. For this one, it's only 1.3. Magnesium chloride, when that dissolves, I get a magnesium ion and 2 chloride ions, so 3 particles for every formula unit. Here's our expected Van 't Hoff factor and the actual. What's going on? Well, it's ion pairing. So when you get ions that pair like this, they act like one particle, and so that reduces the effective number of particles in the solution. For FeCl3, there's 4 particles. So there will probably be a question on the exam which uses the Van 't Hoff factors, and these actual Van 't Hoff factors would be given to you. You don't memorize those, not at all. The only thing you should know about the Van 't Hoff factor is that it'll be less than what we expect. What you should be able to predict and use if necessary is the expected factor. And you get this expected factor just by looking at, well, how many ions does this form when it dissolves? 1 formula unit of FeCl3. We should be able to recognize that we've got Fe3 plus ions and chloride ions, and there's 3 of them. So it's a total of 4 particles, 4 ions. The Van 't Hoff factor is going to be different at different concentrations, and so that's why this is specified at 0.05 mole concentration. But we don't have to worry about other concentrations. So when we have ionic solutions, we need to apply that Van 't Hoff factor for each of these: boiling point, elevation, freezing point, depression, and osmotic pressure. And so the equations are the same, we just throw that factor in front. Right, you should be able to figure out the expected Van 't Hoff factor, By looking at the chemical formula. Yeah. Yes?
In order to get the expected, you need to do
No.
Okay.
No. What we're looking for is this: the moles of particles, so ions, divided by the moles of formula units. So we're looking at the chemical formula. Let's look at this one, K2SO4. If one unit dissolves, how many ions do I get? I get 2 potassium ions and 1 sulfate ion, that's 3. So the Van 't Hoff factor expected is 3. So we should be able to answer questions like this. Which aqueous solution has the highest boiling point? So this does not have anything to do with intermolecular forces. Because the solution here is aqueous, it's all water. Water with something in it. So the water will boil at a higher temperature when it's got more solute in it, right? So to find the highest boiling point, we're looking for the highest concentration of particles. You notice that all 3 solutions are the same molarity, right? I'm not sure why the first one has a 0 and the others don't. I think that's a typo. Like, well, they're all the same concentration, but are they non-electrolytes or electrolytes? This is carbon, hydrogen, and oxygen. I don't expect you to recognize that that's a sugar, but does that look like an ionic compound? No, 3 nonmetals. That's not ionic. So this is a molecular compound. That's going to be a non-electrolyte. What about sodium chloride? Is that an ionic compound? Yeah. So this is an electrolyte. It's ionic compound. How about MgCl2? Is that ionic? Yeah. Magnesium's a metal, chlorine's not. So this is also an electrolyte. So when we have electrolytes, they separate into particles, and so they produce more particles. So we can eliminate the sugar solution as not having the highest boiling point, because when a molecule of sugar dissolves, you just have one molecule. You don't get multiple particles. When sodium chloride dissolves, what do I get? I get sodium ions and chloride ions. Oops, I don't know where that came from. How many ions is that? 2. Get 2 ions. So my expected Van 't Hoff factor would be 2. What about MgCl2? Get Mg's 2 plus and 2 chloride ions, right? So that's 3. Now we know that the actual Van 't Hoff factor is a little bit less, but this is good enough to allow us to compare which one's going to have a higher boiling point. C, the one with more particles. Any questions? Occasionally in the test bank, they have problems like this where they have different concentrations and different compounds, which makes it a real bear of a problem. I will avoid asking ones like that. Mm-hmm. Yeah. If these both had produced 3 ions, the only difference would be in the actual Van 't Hoff factor versus the expected, and there's no way you would know that. So I wouldn't ask you that one. Calculate the freezing point of an aqueous 0.10 molal FeCl3 solution using a Van 't Hoff factor of 3.2. So the Van 't Hoff factor is given to us here. Looking at the compound formula here, FeCl3, what factor would we expect it to have? 4. Because you get an iron ion and 3 chloride ions, that's 4 particles. We expect it to be 4, but it's actually 3.2. So we're supposed to calculate the freezing point. So we're going to use the freezing point depression the freezing point depression equation. But we're given a Van 't Hoff factor. This is an ionic compound, so we need to use that. So we've got that Van 't Hoff factor times the molality times the freezing point depression constant. So I is equal to 3.2. That doesn't have a unit. The molality was given to us, 0.10 molal. And Kf, we would look up, 1.86 degrees Celsius per molal. Zero 0.5952 degrees Celsius, 2 sig figs. Yeah. Correct. Because it's the number of particles divided by the number of formula units. It's just 2 numbers without really a unit. So how do I use the change in freezing point to calculate the actual freezing point? I have to subtract this number from the freezing point of pure water, right? And, it feels a little dumb drawing thermometers, really sad-looking, wobbly thermometers, but when we go around 0 and we're subtracting and there's positives and negatives, it's really easy to screw up. And if we look at it more like a number line, a thermometer really is a number line, then we're less likely to screw it up. So freezing point depression means that the freezing point is below what it should be. And the difference is that number I calculated. And so I would say that the freezing point is equal to negative 0.60 degrees Celsius. Any questions? You do the same type of calculation with boiling point elevation or with osmotic pressure. So we also talked about vapor pressure lowering, and strong electrolytes are going to have a larger effect on vapor pressure lowering as well. And so if we're trying to calculate the vapor pressure for a strong electrolyte solution, we need to account for the dissociation when we're looking at the mole fraction. So let's do an example of that. A solution contains 0.115 moles water and an unknown number of moles of sodium chloride. The vapor pressure of the solution at 30 degrees Celsius is 25.7 torr. The vapor pressure of pure water at 30 degrees Celsius is 31.8 torr. Calculate the number of moles of sodium chloride in the solution. Well, let's pull some numbers out. So we have 0.115 moles of water. We've got a temperature of 30 degrees Celsius. We've got a vapor pressure of the solution, so I'm going to call that P solution, is 25.7 torr. And the vapor pressure of pure water is 31.8 torr. Well, what was the equation for vapor pressure lowering? the vapor pressure of the solution was equal to the mole fraction of the solvent times the pure vapor pressure of the solvent. Okay? So then here our solvent is water. So this is the vapor pressure of the solution. That's the P solution. So we have P solution and we have the vapor pressure of the pure solvent. So we could solve for the mole fraction of water. The mole fraction of water is going to equal the vapor pressure of the solution divided by the vapor pressure of pure water. So the solution was 25.7 torr. Pure water was 31.8 torr. The torrs cancel out, which is as it should be. 25.7 divided by 31.8. 0.808. So great, we calculated a mole fraction. It wants the number of moles of sodium chloride. Well, yeah, the mole fractions of the two things do have to add up to 1. There's a couple of ways we could get at this. So we've got sodium chloride. That's an ionic compound. And so it's going to dissolve into ions. So instead of calling it NaCl, I'm just going to call it ions to help me not forget that I have to mess around with that. So the mole fraction of the ions in the solution plus the mole fraction of the water does equal 1. I think it might actually be easier to do it the other way. So I'm looking at the mole fraction of water is equal to the moles of water divided by moles of ions or particles plus moles of water. I know the mole fraction, I know the moles of water, and so I can solve for moles of ions. We're going to need a little space, so I'm going to go up to the top. So this is one because we've got adding and dividing. It might be easier for you to put the numbers in first and then solve it. So the mole fraction of water is 8.80817. And that's equal to the moles of water, which was given to us, 0.115 moles, divided by moles of ions plus moles of water. It's kind of need more room than I've got. So I've got this number times moles of ions plus 0.115 is equal to 0.115. So this is in parentheses. I have to distribute this. let's, instead of writing moles of ions, let's call that X. Okay with that? We'll make this X. So I've got 0.80817 times X plus 0.80817 times 0.115. So that gives me 0.09294 is equal to 0.115. If you're good at algebra, you can do this without writing everything out, but it's a good idea to write it out. 0.80817x is equal to 0.115 minus 0.09294. So that equals 0.022056, something like that. So then to solve for x, I need to divide both sides by 0.80817. X equals 0.02729. I think this actually is now two significant figures. Moles of particles of ions. But we want moles of sodium chloride. .02729 moles of ions. I want moles of sodium chloride. How many moles of ions do I get from 1 mole of sodium chloride? 2. I get a mole of sodium ions and a mole of chloride ions, so 2 moles of ions. So I'm going to take that number and divide by 2, and I should get 0.013647 moles of sodium chloride. With sig figs, I could be wrong, but I think it's 0.014 moles. That's a little more involved. Yeah. It is possible you could have something like this on an exam. It could be not multiple choice, yeah. This, I prefer to, what did you say?
I said it seems like a problem.
It does, yeah. I think these are fine, but I'm weird, I know that. This is actually, I prefer to have something like this as a write it out problem rather than a multiple choice, because there's so many little pieces here, right? And you get one thing wrong and you choose the wrong answer in multiple choice, you get 0 points. Whereas when you write it out, if you got most of it right, it might be worth 4 points. I'll give you 3 if you had that one little mistake. If you wrote down anything remotely related to the problem, I'd probably give you at least 1 point out of 4. You leave it 0, then you got 0. Right. So these equations will be given on my exam. Yeah. And when we look at the final exam, we'll see that most of the questions don't involve using specific equations. And so if there was a question about vapor pressure like this, it would not be this long calculation. It'd be more of a conceptual question that you could answer by understanding the process without remembering the exact equation. Yeah. Because they don't really give you any equations on the ACS exam. I think it's 70, but I can't remember for sure. So 0.014. Colligative properties are important in the field of medicine. So when you're giving an IV fluids to a patient, it's very important that the concentration of particles in that IV fluid matches up with the concentrations of particles inside the cells of the person, right? So we can look at this in terms of osmotic pressure. So we can talk about hyperosmotic or hypertonic solutions. This is a more medical term. There's isotonic or isoosmotic and hypo. So hypo is below, iso is the same, and hyper is above. So if we have a hyperosmotic solution, this has a greater osmotic pressure than the bodily fluids. It has a larger concentration of solute particles. And so here's our normal red blood cell. And if we're in a hyperosmotic solution, it will draw water out of the red blood cell, causing the red blood cell to shrink up and get all spiky. I think it's on the 3A ACS exam, but that's called crenation. So that could be on the final exam. I think it's on the 3A exam. It's not in the book, and so I always try to make a point of saying it so that you have a clue if you have it on an exam. If we have a hypoosmotic solution, say if you gave IV fluid that was pure water, that would be really, really bad because then the cells absorb water. It's always trying to equalize the concentration. So that it goes from the higher concentration solution into the lower concentration solution. And that causes the red blood cells to swell up. And if that continues, then they'll burst. And that's not good, right? So what you want is a isoosmotic or isotonic solution where the concentration of particles is the same as what's in your body. And they have to consider the total particles. So if they're an IV solution probably has some sodium chloride in it and probably some sugar. And so they have to consider the combination of all the different particles in the solution to figure out that it's isotonic. By the way, if you're trying to clean blood out of clothing, not that anyone's, like an axe murderer or anything, but blood happens, right? You can take advantage of this. If you take the bloody thing and you soak it in water, pure water, the blood cells will expand and burst, and then they'll wash away much easier. Cold water for removing blood. Just, a little bit of experience with children bleeding on things. So hypoosmotic or hypotonic solutions have lower osmotic pressures. They're going to cause the cells to burst. So isotonic saline is 0.9 grams per 100 milliliters of solution, which is a 0.9% mass to volume. And that's a common unit in medicine, is a mass to volume percent or a mass to volume ratio. So if you're given just pure saline, it would be 0.9%. If they're going to add something else into there, then the saline concentration would have to go down in order to account for the particles of the other solute, maybe sucrose or glucose.